Now let's talk about the properties of a correlation coefficient. Again, a correlation coefficient is always going to be a value between -1 and 1, including -1 and 1. In other words, R is greater or equal to -1 and less than or equal to 1. Now, what if you have R equal to 1? What if the correlation coefficient is equal to 1? In this case, you would have a perfect positive linear relationship. Now, earlier I mentioned that the correlation describes the strength and the direction of the relationship between the two variables. And so here, notice we are seeing R. Okay? Notice here, we have a R value that is positive. Thus, we have a positive linear relationship. And here we see that R is exactly 1. That means we have a perfect, or you can think of this as a really, really, very, very strong linear relationship. If somebody's telling us that the correlation coefficient is equal to 1, we should be visualizing a scatter plot where the points create a perfect line with a positive slope. If we use technology to find the regression model for this scatter plot, we're going to see that the regression model touches all the points on the scatter plot. Now, think about it. In real life, it would be really rare for us to collect data and to see this perfect positive linear relationship. Now, what if R is equal to -1? Well, in this case, we still have a perfect linear relationship, or you can think of this as a really, really strong linear relationship. But notice the R value here is negative. In this case, we would have a perfect negative relationship. If we're being told that R is equal to -1, we can visualize the scatter plot having points such that the points create a perfect line with a negative slope. If we go ahead and use technology to find the regression model for this scatter plot, we're going to see that that regression model is going to be touching all the points on the scatter plot. Again, in real life, it would be really rare to see such relationship. Now, in real life, you might have a correlation coefficient that is somewhat closer to 1 or closer to -1. Now, the closer R is to 1, the stronger the evidence for a positive linear relationship between the two variables. So you can give yourself some examples. So we could say, what if we have something like R equal to 0.9? If we look at this value, we see that it's close to 1. So we're expecting to see a strong positive linear relationship. Or maybe something like R equal to 0.8. R equal to 0.97. We would be looking at that correlation coefficient. We would be saying we're going to see a strong positive linear relationship. Now, the closer R is to -1, the stronger the evidence for a negative linear relationship between the two variables. And again, you can give yourself some examples. Here we could have, I'm just going to use the same values as above. We could have R equal to -0.9, R equal to -0.8, R equal to -0.97. We're seeing that these values are close to -1. So we're expecting to see a strong linear relationship, but this time we're expecting to see a negative linear relationship. If you see that R is closer to 0, the closer R is to 0, the little or no evidence of the existence of a linear relationship between the two variables. So if you have something like R is equal to 0.0, if we had this R value, we would be thinking we might not have a linear relationship. There's little evidence for us to claim that there's a linear relationship. It might be the case that this value is positive or negative. In both cases, we would say there's little to no evidence that there exists a linear relation. Let me give you more examples. R equal to 0.21 or R equal to -0.1. Those values get closer to 0. Here again, we're thinking there might not be a linear relationship. Now, be careful. When we're talking about R, we're talking about a linear relationship. This R value describes how strong the linear relationship is and the direction of that linear relationship. So when we see that R is really close to 0, We're going to say that there's no linear relationship. Okay? There might be some other type of relationship. And I can give you some examples here. It could be the case that you're looking at a scatter plot, and that scatter plot creates the shape of a parabola. If I try to model this scatter plot with a linear function, my R value is going to be close to 0. Again, we would not say that the variables don't have a relationship. We would say the variables do not have a linear relationship. This scatter plot has a quadratic relationship. I can give you other examples. It might be the case that you see an exponential relationship. If we try to model this scatter plot with a linear relationship, we're going to notice that R is really close to 0, which means that there's no linear relationship, but it doesn't mean that there's no relationship at all. For this scatter plot, we would say that the variables have an exponential relationship. So we're going to be careful with the language we use. Now, another thing that I want to mention, and we have seen this before in an earlier chapter, really early during the quarter, recall and be cautious about this, that the correlation does not imply causation. What we're saying here is that we're not going to assume that one variable is causing the other just because there's a correlation between the variables. For example, if you're seeing that as your X values increase, your Y values increase, it doesn't mean that X is causing Y to increase. It might be that there's some other factors that are causing your X value and your Y value to both increase. Okay, so there's some other explanation of why we're seeing this correlation, but we do not say that one variable causes the other one to behave a certain way. Now, after looking at the properties, we are ready to play this game here, where we're going to be matching each of the scatter plots shown below with one of the correlation coefficients we have here below. How should we start? We can go ahead and look at the graphs and try to find the correlation coefficient. We could also look at the correlation coefficients and try to match them with the graphs. Let's start by just looking at the graphs. Notice here, let's start with the easiest ones. So here in graph D, we see a scatter plot where the points create a perfect line, and this line has a positive slope. This is what we would call a perfect linear relationship, and we would also say that this is a positive linear relationship. So here, for this graph, we're expecting a positive R value, and we're expecting that R value to be 1. And so notice here, we have R equal to 1. That is the correlation coefficient for graph D. So I'm just going to write R equal to 1 here below the scatter plot. Again, we're going to take care of the easy graphs first. Notice graph H has a scatter plot where the points create a perfect line. This line has a negative slope, and so we're expecting the R value to be negative. Because this is a perfect negative relationship, we're expecting that R value to be equal to -1. Okay? So notice that is the R value we have here in part B. Graph H has a correlation coefficient equal to -1. Now, I'm going to look at graph A and graph E. And I'm starting to look at these graphs because I see a bigger spread. So I'm expecting that correlation coefficient to be closer to 0. And so here in graph A, notice we do see a linear relationship. We do see that as X increases, the Y values increase overall. In graph E, we see a bigger spread. We can't even tell if this would be a negative relationship or a positive relationship. Perhaps we're thinking if we try to use technology to come up with a regression model, that regression model might be in line with where the slope is close to 0, meaning the equation would be a horizontal line equation. Again, we're expecting to see values that are really close to 0. So let's go back to our list. I'm going to circle the values that are really close to 0. So we have this value here. They're the last 2 values that we have here. The other 4 values are closer to 1 and -1. That's why I'm not looking at those. Okay? Both of them are positive. Now here, R equal to 0.08. That one is closer to 0. So the scatter plot with the weakest linear relationship is going to be matched with R equal to 0.08. And in our case, the scatter plot with the weakest linear relationship would be the scatter plot that we have here in graph E. So R here is equal to 0.08. Now the correlation coefficient for graph A would be R equal to 0.33. So we are done assigning those two correlation coefficients to a graph. Now I'm actually going to stop here and let you finish this on your own. I will give you some hints. Notice here, graph B has a positive linear relationship. Graph C also has a positive linear relationship. So we're expecting a R value that is positive for these two graphs. Okay, so think about the R values that you have left that are positive. That would be R equal to 0.98 and R equal to 0.69. So you know that for graph B and C, you're supposed to have a R value that is positive. Now you need to think about which of these graphs has a stronger linear relationship. The one that has the strongest linear relationship should have the R value that is closer to 1. Okay? Now graph F and G have a negative linear relationship. So we're expecting the R values to be negative. And so notice we have two negative values left, R equal to negative 0.92 and R equal to negative 0.64. So here, in order to decide what R value is going to be matched with graph F and G, you need to think about which of these two graphs has a stronger linear relationship. Okay. The graph that has a stronger linear relationship should have the R value that is closer to -1. This game is helping us determine whether we understand the properties of the correlation coefficient. Do we understand that when R is closer to 1, we should have a stronger positive linear relationship? When R is closer to -1, we should have a stronger negative relationship. When R is closer to 0, we have little to no evidence of a linear relationship. This game is helping you assess your understanding of those properties.